Hello everyone. Today we are going to see a lecture on singly reinforced beams. A singly reinforced beam is a reinforced concrete beam that only contains reinforcement in the tension zone. Let us take a cross section of a singly reinforced beam. We know that in the beam the tension zone lies in the bottom and the compression zone lies in the top. If the beam is only reinforced in the tension zone, that is called a singly reinforced beam. However, singly reinforced beams are provided with two additional bars in the compression phase of the beam. These two bars are called hanger bars. These are used to facilitate tying stirrups to the bars. Let us keep B as the breadth of the beam and this distance as D, which is the effective depth. The effective depth is the distance from the centroid of the tension reinforcement. This is the center of rebar in the tension reinforcement to the edge of the compression fiber. So the distance from the top to the center of the rebar is called the effective depth D. Now let us consider a balanced section. In this section, the strain in steel and strain in concrete reach their maximum value simultaneously. This is the strain diagram and this is the stress diagram. Let us keep xu as the depth of the neutral axis from the top. In the balanced section, it will be maximum and this distance will be d minus xu max. Now let us take IS 456 code 2000 page number 69. Let us see the second assumption. The maximum strain in concrete at the outermost compression fiber is taken as 0.0035 in bending. So this strain is 0.0035. The maximum strain in the tension reinforcement in the section at failure shall not be less than Fy upon 1.15 ES plus 0.002. So this should be this distance. Now let us see this assumption. For design purposes, the compressive strength of concrete in the structure shall be assumed to be 0.67 times the characteristic strength. We know that the characteristic strength is FCK, so it should be 0.67 FCK. The partial safety factor 1.5 shall be applied in addition to this. 0.67 FCK upon 1.5 we will get 0.4466 FCK. We can round this as a 0.45 FCK. So this should be 0.45 FCK. Let us take the strain diagram. We can apply similar triangle rule. 0.0035 upon XU max will be this upon D minus XU max. We can take a D minus XU max on the other side and XU max on the other side. We can multiply this with this. This into this, we will get minus 0.0035 XU max. We can take that on the other side, so it will come as positive. We can take XU max outside. 1 upon 1.15, it will be 0.87. We can take D on the other side, it will come in the denominator. And we can take this on the other side, it also will come in the denominator. 0.0035 plus 0.002, we will get 0.0055. ES is the Young's modulus of the steel. In the codebook, page number 70, ES is given as 200,000 Newton per millimeter square. So for ES, we can apply 2 into 10 power 5. For these two terms, we can take LCM. When we multiply these two, we will get this. We can take this in the numerator. 0.0035 into 2 into 10 power 5. It will be 700. So we will get this expression. For different grades, we can find XU max upon D. For FY, we have to apply 250, 415 and 500. In this way, we will get these three values. In the code book also, you can check in the page number 70. Now let us take a random section. In the stress strain curve, we can see that the strain at the end of the parabolic shape is 0.002. In the assumptions, we can see that let us keep this point as A, this point as B, and this point as C. Let us apply the similar triangle rule. BC upon AC should be equal to 0.002 upon 0.0035. Using the calculator, we will get 4 upon 7. We know that AC is XU. We can take that on the other side. So BC will be 4 upon 7 XU. AB will be AC minus BC. We know that AC is XU. BC just before we have found. For AB, we will get 3 upon 7 XU. Now we are going to find the compressive force that will be within the area of the stress diagram. In the stress diagram, there are two parts. First, the rectangle. Let us keep this as number 1, and then the parabola. Let us keep this as number 2. Let us find C1. We know the width of the beam, that is B. We know the area formula of a rectangle, side into side. This side is AB. We have already found that 3 upon 7 into XU. This side is 0.45 FCK. For C1, we will get this. Now let us find C2. This is the parabola. Area of this parabola is 2 upon 3 into BH. Here the breadth is BC, which is 4 upon 7 into XU, and the height is 0.45 FCK. For C2, we will get this. To find the compressive force C, we have to add C1 and C2. When we do that, we will get this. We need to find the centroid distance of this shape, but it is a little difficult. As before, we have to split this into two parts. First the rectangle and the second the parabola. We have to find the distance y1, that is the distance from the center of the rectangle to the top. We know that totally this is AB, which is 3 upon 7 XU. When we divide that by 2, we will get the distance from the centroid to the top. Let us find y2. Let us assume that the centroid for the parabola lies here. The formula to find the distance from the centroid to this point is 3 upon 8 into breadth. Here the breadth is BC, which is 4 upon 7 XU. So it is 3 upon 8 into 4 upon 7 XU. But we have to find the centroid distance about the top. So we have to add the remaining distance, which is AB. We know that that is 3 upon 7 into XU. For y2, we will get 0.643 XU. Now we need to find y bar. Using this formula, we can find y bar. For that, we will get 0.42 XU. Also, we have found the compressive force. In the code book, page number 69, we can check these two. Now let us find the tensile force. We know that stress is force by area. So force will be stress into area. In the tension area, we have the steel. The area is AST and FST is the stress in the steel. That will be Fy upon 1.15, which is 0.87 Fy. For the tensile force, we will get 0.87 Fy AST. To find the actual depth of neutral axis, we have to equate the compressive force and the tensile force. In this way, for XU, we will get 0.87 FYAST upon 0.36 FCKB. Now let us define lever arm denoted by Z. It is the perpendicular distance between the line of action of the couple forming compressive and tensile force in a reinforced concrete section. The lever arm Z will be D minus 0.42 XU. Now let us find the moment of resistance with respect to the tensile force. We need to multiply the tensile force with the lever arm. So we will get this. For XU, we can apply this. We can take 0.42 into 0.87 upon 0.36 approximately equal to 1. In this term, we can multiply the numerator and denominator with D. Then we can take D outside. The same equation can be found in the code book, page number 96. This equation for moment of resistance should be used only for under-reinforced sections. Now let us find the moment of resistance with respect to the compressive force. The formula is C into Z. We can apply both of them. Now let us find the limiting moment of resistance, because in the over-reinforced sections and balanced sections, we have to use XU max instead of XU. In this term, we can multiply the numerator and denominator with the D. Then we can take this D outside. Then we can divide on both of the sides by FCK BD square. FCKB can be eliminated. This D and square will be eliminated, so that we will get this equation. Previously, we have already calculated XU max upon D. Instead of these, we can apply these, so that we will get this. We can take FCK BD square on the other side, so that for these three grades, we will get the limiting moment of resistance. Now we are going to see the differences between balanced section, under-reinforced section, and over-reinforced section. We know that in the balanced section, the stress in concrete and steel will reach their maximum value simultaneously. In this case, XU will be equal to XU max. Using this, we can differentiate under-reinforced section and over-reinforced section. When XU is lesser than XU max, that section is called under-reinforced section. When XU is greater than XU max, that section is called over-reinforced section. Now let us elaborate under-reinforced section. We know that when XU is less than XU max, that section is called under-reinforced section. In this section, the percentage of steel is less. We know that the steel is expensive, so this design is more economical. Steel will yield and failure will occur again due to crushing of the concrete. Since steel is yielding first, the beam will show considerable deflection, so that we will get enough warning of failure. Using this equation, we can find the moment of resistance, or we can use this equation. Now let us see the over-reinforced section. When XU is more than XU max, that is called over-reinforced section. Here the percentage of steel is more, so this design is uneconomical. Steel will yield first and failure will be due to only crushing of the concrete. So there will be no warning signs and the failure will be sudden collapse. So we have to avoid this section. This section is not recommended. Using this formula, we can find the limiting moment of resistance, or we can use these three formulas. We know about the balanced section. Here XU will be equal to XU max. Using this formula or these three, we can find the limiting moment of resistance. Now we are going to make the expression for the area of the steel in tension and the percentage of steel upon 100 in the under-reinforced sections. We have derived this formula. We can take 0.87 FYD on the other side, so it will come in the denominator. With this, we can multiply AST. 1 into AST, it will be AST. AST into AST, it will be AST square. We can take these two terms on the other side, so they will come with the change of signs. This is a quadratic equation. Using this formula, we can find AST. A is this one, B is -1, and C is this one. 4 by 0.87, it will be 4.6. We can eliminate Fy. D into D, it will be D square. Here we have plus or minus. The positive sign is not applicable, so we can only use the negative sign. We can take this term inversely. 1 upon 2, it will be zero point 0.5. This is the formula to find AST directly. We know that the percent of steel is 100 AST upon BD. So AST will be PTBD upon 100. Instead of AST, we can apply this. We can eliminate BD. So this is the expression for PT upon 100. From this, we can write PT upon 100 is AST upon BD. Now we are going to end this session. Thank you for watching this video.